Greetings, ladies and gentlemen, and welcome once more to the Compendium of Mad Science. Today is episode 2 of the Compendium of Mad Science, and we're going to be looking at the Fluke 6160A frequency synthesizer. So this is the Fluke 6160A frequency synthesizer. It seems to be in pretty good order. Most of the frequency ranges work correctly. However, it's got an issue with the lowest frequencies. If you try to go below 3 MHz, it increases the signal by 2 MHz, making it impossible to go below. To do this, we're going to need an oscilloscope. And in order to check we have the right frequency, a frequency counter. Right, so turning it on, you can see that you immediately get a signal. I'll just turn on the frequency counter on here. As you can see, it's about 2.5. However, this is actually set to 0. If you increase it by 1, it increases by 1. Increase it by 2, it goes up by 2 to 2.5. And this is where things get interesting. If you add some of this on to take it up to 5 MHz, it drops back down to where it's supposed to be. Again, you can see that if you drop up to 3 MHz, it does actually set. But if you go down, it offsets the measurement by 2 MHz. And I have no idea what's causing it. I suspect it's either something to do with the controller board. I'll show you inside. There's a big board at the right here used for, it's a control computer or frequency control computer, I think they called it. Or it's something to do with the pots on the front here, but I don't imagine. But given what I've seen so far, I don't imagine that's the case. These are really nice feeling knobs, by the way. Flick this up to 1, it drops back down to where it's supposed to be, and then you can set it correctly after that. All the other ranges work perfect right up to the maximum frequency of just under 30 MHz, which makes it convenient for hams working in the HF region. I see 2.999881. Bearing in mind that reads a little low, it's probably pretty close to 30 MHz. But I don't know what the frequency counter on this says. It says 3.01. Doesn't seem to want to stabilise. It's saying 3.330, so I'd assume it's more or less correct. Again, the frequency counter on this isn't the best, but it's good enough for Grandad. On the back here we also have a couple of other connections. The 1 MHz derived frequency seems to be working fine. It's coming through at 999.955 kHz, which is good enough for me. So within the range of my measurements, my measuring gear rather. And the other reference seems to be coming through at 999.995 kHz. Again, 100 kHz, 0.1 MHz, good enough for me. Finally, we have the 5 MHz reference. I believe this is an uncontrolled reference. I'll need to take it apart and have a look. And this should be at 5 MHz. Again, 4.99976. Well, 4.999 MHz. Good enough for me. Now, trap for young players, or whatever Dave Jones says. I appear to be copying him just now. Now, quick trap to look out for. This signal here is due to me using the wrong type of coax. This is all 50 ohm gear, and this is 75 ohm coax because it's what I have on hand. I have lost my 50 ohm coax leads. I don't know how I managed it. See, the sinusoidal waveform isn't perfectly sinusoidal. The falling edge is slightly steeper than the rising edge, but again, it shouldn't really matter as long as the peaks are where they're supposed to be. I say it shouldn't really matter. I don't believe it should matter. I could be entirely wrong. The main board here is the frequency control computer, and It's quite a nice little design here. I pull up the entire board, and that exposes the top end of the motherboard. And again, the opposite side comes up as well. There's a couple of voltage rails on here, connection to the controller board. Back end here, all that's to do with the power supply. At the front, we've got the back end of 3 big bypass caps. Those are actually screw terminals for them. At the front here, you have a variety of voltage rails coming off. Some of those are going to the back end. Some of them goes across the back end here. We can see a number of turrets connected to the back of the digital signal module. Again, at the front here, you've got a couple of extra connections coming from the front. These are just voltage connections. And there's a couple of extra rails here which go to the back. On the opposite side of that is another power supply unit. So the back of this just pops off. MJE 3055s here, and a couple of D4 405s below them. These are both power transistors, and up in the top left here we've got a GE D4 505, so we have an MJ2955. That's also a switching tranny. I quite like the design here, as in the whole, if you want to test these, you can take the whole back panel off and test them without having to go inside the unit. But then again, that's only useful if you know what the problem is. So at the bottom here we've got a common mode choke. Over here are the connectors going to the front of the board there, the control board. Fanning up from that, these are SN741004s. These are 74100N 8-bit bistable latch. And there's 5 of them in this board. 4 here and one up a bit further up. Now, interesting to note is that, find my pointer. Interesting to note is that someone has actually scratched an arrow onto these, which makes me think someone's had a go at repairing this. So if there is an issue, it's possible it's on this board, unless they've actually done a good job of fixing it, in which case, well, the issue's gone. Directly above that is a nice little gold-plated chip. That's an Motorola MC4001P, which is a BCD to binary and binary to BCD number converter. The next 2 chips are ITT 936-5Ds. I've not been able to find a data sheet on these yet. Another 4001P. I've not been able to make this one out very well. It's a 946-DC, produced in the 42nd week of 73. Up here we have an SN7470N, which is a dual positive edge triggered JK flip-flop, flippity-floppity. On the next row we have a series of, I can't read that, SN7493, which is a decade divide by 12 counter. You'd do all this in a single microcontroller nowadays, to be honest. As you see, there's been quite a few little repairs made to this board, particularly that little guy, that ITT 7404 part. Looks like someone's had a little hack at those pins. Can't say I blame them, because these other pins are pretty damn messy. Some of them are incredibly rusty, and a lot of them look like they've gone black. I'm not sure if they're originally black, or if it's nickel coming out of the leaching out of the metal. Either way, the whole board's definitely seen better days. But then again, this is a 1973 board, which makes it considerably older than I am. Right, the bottom side's where all the magic happens. Oh, let's have a look-see. This down here is the module set. This is a 0.1 MHz digital generator. Let's see, we've got a couple of badges up here. Step LP, voltage control oscillator, PHDT, is that a phase detector? And the top one's not numbered. It would appear to be the 364810. It's not marked with anything apart from that. Interestingly enough, it may not actually be part of the rest of the module, which is interesting. I'm going to try to avoid taking these ones apart if I can help it. If you want me to go back and have a look inside them for you, just give me a shout. Leave it down in the comments and I will certainly consider it. So this is where a lot of the magic happens, I believe. I'm not entirely sure what this board is for, which is why I believe the magic happens there, because if I don't know, it must be magic, obviously. Those are the three big caps with the screw terminals I was talking about earlier. Power supply at the back, and down here we have the, let me get my pointer, we have the, I believe that's an oven controlled oscillator, Vectron Laboratories. That's a 5 MHz reference, by the way. This here is the power supply. It's helpful I had it in shot. A couple of metal cans at the back. Is that tantalum? Very nice colour, I'm used to them being bright yellow. So what are these? I've never seen that before. Is that looks like a capacitor, but I'll just zoom in on that. So capacitor with red, white, yellow, black, or black, yellow, white, red, depending which way you want to read it. Is that a colour-coded capacitor? Cute. Over here you can see a couple of big wire-wound resistors. These are obviously precision trimmed. I think they're 5 kHz. Sorry, 5 kHz, 5 kilo ohms. Yep, 5 kilo ohms, individually marked. Although the other one at the back's not actually marked. Now, interestingly, in this, you'll see there's actually the imprint of 4 headers at the top here, which confuses me because I don't have that many headers inside. So this was sitting, obviously, let's move this over. Obviously, this was sitting over here, and we don't have 4 sets of headers. 4 sets, we don't have 4 headers sticking up. So I believe this was taken from another unit. And interestingly enough, this is removed from U273 faulty. So this makes me think that this particular module is faulty, and this may be contributing to all our problems that the front end seems to be having. So let's open it up, see what we got. Oh, there we go. Ain't that pretty? This is the output divider, apparently. One of these transistors up here has had a replacement at some point. Looks like this was probably a commercial or industrial unit. I'll just flip this around again so we can read the ICs. So I've got MC1032P. Righty-ho, not sure what that is, I'll look it up in post. Got on the ITT, this is at 946EN. Over here we have a bunch of passives. Inductors, are those inductors? Yeah, they are. Sorry, the little red cylinders were throwing me, I've not really seen them in that package before. Lots of passives, inductors, capacitors, you name it. And once again, we've got a very big painted capacitor at the back here. And once again, beautifully painted. Gorgeous, no? RF shield. Now you got that right. At the back there, I got a couple of active parts. Oh, there's a nice little loop, look at that. Isn't that pretty? It's a controlled impedance loop. It's the only reason I could think that you'd want to bring it out that far away from the capacitor. I just noticed this thing sliding. Another nice colour of capacitor there. Hey, that's seen better days, hasn't it? Ugh. What's that? Oh, I missed that chip, didn't I? Oh, that's the ITT chip that we saw earlier. And there's just our voltage rails coming back in from the side. Apart from that, there really isn't much happening at all. Most of the board's empty, which is interesting. Looks like it's almost entirely. In fact, I'll tell you what that might be. These numbers here. This might be another series of boards. Yeah, in fact, that looks like, if you look, there's like a number of channels here. That'll just be repetitions of that, and they're pulling it along and shoving it over. So obviously this can do other, it's either an extra board or add-ons you can get for it. Right, and I think that will do us for this teardown. There's not really much else I can say on this, it's not already been said. This was the Fluke 6160A frequency synthesizer, and we'll be back next week, hopefully, with a new segment based on microscopy. Until then, have a nice evening. If you enjoyed the video, why not leave a like? If you want to talk about it, leave a comment. And if you want to see more, feel free to subscribe. Hi, this has been your resident mad scientist, Callum P. Robertson. And this is the Compendium of Mad Science. Good night, folks.